Now let us proceed to the next problem here. So for the next problem is we are dealing now with the axial deformation. So we have here axial deformation. So let us just apply the principle we have learned on delta. It's just simply equal to PL all over AE. So first we would like to draw or figure here. See, we have established our ceiling. On the ceiling, this rod is hanged, okay, on that ceiling. So this has a dimension equivalent to 150 millimeters according to the problem. Okay, so we have here 150. millimeters. So what are the given here? We have 7,850 kilogram per cubic meter. So 7,000, that is identified as the density. We have 7,850 kilogram per cubic meter. So how shall we relate to this? Just imagine the units here. In order to come up with a weight, we'll have to eliminate cubic meter here by multiplying it to the volume. So if this cubic meter here is being eliminated, the resulting unit would be equal to kilogram only. Isn't it? So what is kilogram? We all know that kilogram is a unit for mass. Now going back to this formula, force is equal to mass times acceleration. So just replace that by W, and then this is mass. Of course, weight is caused by a downward force, acceleration due to gravity. So this is the general formula for the weight. So of course, first our objective is to come up with the unit mass by this rho. Okay, so by the unit itself, it tells us that mass is equal to rho times volume. Why? Again, we have to eliminate this cubic meter in order to come up with a unit kilogram only. So how shall we eliminate this one? If we are going to multiply it by the volume, then we can come up with the kilogram only. That is why this is rho times the volume. Okay, so I hope that is clear. So mass here is equivalent to 7,850 kilogram per cubic meter times the volume. Of course, we need to have the area. Of course, the area is given here. Okay, 300 millimeters squared. So, however, it is expressed into millimeter. So supposedly we should express that in cubic meter. So again, let us recall the conversion factor here, that 1 meter is equivalent to 1000 millimeter. Now the given here is 300 millimeters squared. Okay, so we're going to multiply this by a conversion factor containing a denominator of millimeter. So just use this. So 1000 millimeter, there is 1 meter. Okay, so since this is squared, of course we're going to square it also correspondingly the values to cancel this. Okay, so therefore this now volume is equivalent to 300 all over 1000 squared. So this is now meter squared. So this is the area. Okay, this is the area. This is the area. This is the density. So we still need to multiply this by the length in order to come up with the volume, since volume is equal to area times length. So this is basic. Okay, so we have to multiply this further by the length equivalent to the total length, 150 meters. So all in all, this will combine, becomes cubic meter divided by cubic meter. So we come up with the mass. Finally the mass is obtained there. So we have 7,850 times 300 times 150 divided by 1000 divided by 1000. 7,850 is 300 times 150 divided by 1000 squared. So we have a mass of 353.25 kilograms. So the weight, we'll just have to multiply this by acceleration due to gravity, equivalent to 9.81. We have 3,465.38 newtons. Okay, So next, we have now obtained the weight on this. Of course, since this is hanging, let me have an illustration for its FBD considering the weight. Okay, so if this is the FBD, there will be a corresponding weight acting on the center of gravity, and the center of gravity is just at the centroid of this one. So in short, we have a downward force here acting on the centroid. And where is the centroid? At the half of the dimension, of course. So let us illustrate that one. So we have here half the dimension. So this is the location of the centroid. Okay. And this is 75 millimeters. Okay. So while we are hanging this rod, W here tends to pull this down, stretching the upper portion. Okay, so it will stretch actually the upper portion here, the upper portion only, because the weight is concentrated on the center or on the centroid. So the lower portion is not subjected to stretching because again W is at the center. Only the upper portion of this rod will be subjected to stretching, and it will stretch the upper fiber of this material. Okay, so let us label this as delta caused by the weight. So this is delta caused by the weight. Okay, so aside from the weight, so since this rod is subjected also to a tensile load of 20 kilonewton, so this is according to the problem, aside from the weight, it is subjected to a tensile force. Okay, so let us again draw another FBD indicating another force. Okay, see, this is the rod. So again, let us label the force the edge, lower edge of this rod. So this is P. So this time, if we subject this rod into force equivalent to 20 kilonewton, the entire length now is subjected to stretching or elongation. So by this, we will be having a deformation at the bottom fiber of this rod. Okay, see, this is the bottom fiber of this rod. say this is delta due to P. Okay, so out of this there will be two deformation or two elongation. Number one, it is caused by the weight, and the other one is caused by the pull at the edge of this rod. So therefore, you can say that the total deformation or the total stretch is caused by delta caused by the weight and delta caused by the pull at the bottom. So all we have to do is to apply the formula here. So this is PL over AE of the weight plus PL over AE of the pull. So we just have to substitute values. So what is P here? Caused by the weight is the weight itself, 3,465.38. What is the length? So the length involved is not the entire length but only the half or the upper half of this rod. So that is, so I think the given is in meter. Sorry about that. We'll have to correct this one. Okay. So this is 150 meters and the other is, or the half is 75 meters. So if that is in meter, therefore it should be expressed into millimeters. So this is 75,000 plus pull due to 20,000, okay, times the length. We have the entire length, okay. So the difference is that the length involved in the pull due to its self-weight is that 75 meter, the upper level is subjected to the elongation, while that of the pull at the bottommost portion will subject the entire length to pull and stretch at the bottom portion. So perhaps we can merge the denominator here because it has the same cross-sectional area as well as a homogeneous material all over the entire length. So the area here, we're gonna just place that one. This is 200,000 or 200,000 megapascal. Finally, we have the total deformation equivalent to 54.33 millimeters. Okay, so very easy problem. So in here, in order to avoid mistakes, we should have to be consistent in the units. So this force here is expressed into Newton. All the forces are expressed into Newton. And then all the distances is in terms of millimeter. So this is millimeter squared, and this is Newton per millimeter squared. So consistently we have used Newton and millimeter as well as Newton per square millimeter, wherein this is actually megapascals. Okay, so I hope this helps for this first problem on axial deformation. So stand by for the next problem. Thank you.